we will go to the fifth and last lecture of week 9. In this lecture, I will do a recap of what we learned this week and then do some practice problems. So, week 9 lecture 5 will be recap of week 9 and practice problems. So let us quickly recap what we learned. In this week, we continued the discussion on X-ray diffraction. In fact, we learned how to analyze X-ray diffraction patterns, and then we talked briefly about X-ray crystallography and electron microscopy. So, in more detail, we learnt about the X-ray diffraction pattern. We saw how to use Bragg's law and what are the factors affecting the intensities, like the temperature factor, the Rietveld factor, the atomic form factor, the geometric structure factor. And then we saw how to calculate the geometric factor and how the geometric factor can explain missing peaks in X-ray diffraction patterns. Then I talked about X-ray crystallography and electron density maps, and finally, we talked briefly about electron microscopy. Okay. So, now let us do a couple of simple problems, okay, that will give you an idea. Okay. So, the first problem relates to analysis of XRD patterns. A certain compound is observed to give peaks in the XRD pattern at 2 theta values. Okay. These are the 2 theta values in degrees. So, you are asked to assume a cubic cell and identify the type of structure, the lattice constant, and to index the peaks. Okay. So, what we have, we will make a little table. So, so we have 2 theta values. We have we have 2 theta values of 42.2, 49.2, 72.0, 87.3. Okay. And what we will do is we will calculate their corresponding theta values. That corresponding theta values is just half of this, 21.1, 24.6, 36.0, 43.65. Okay. Now, what I am going to do is the following. Remember the Bragg's law. Okay. So, the Bragg's law says that lambda equal to 2 d sin theta. Okay. And in particular, for a cubic crystal, cubic implies d is equal to a divided by square root of h square plus k square plus L square. Okay. And so, in other words, I can say that so if I substitute for d and then I multiply out, and I can write this in the following way. I can write that sin square theta is equal to h square plus k square plus L square, okay, divided by, okay, I will just write it as divided by, and what I have in here is a by 2 lambda square. Okay. So I will just write it this way. So basically, what I want to say is that sin square theta, now a is fixed for the lattice, lambda is fixed for the lattice. So sin square theta is proportional to h square plus k square plus L square. Okay. So what we will do is we will make a table and we will write sin square theta. Okay. Now, if I calculate sin square theta, so for 21.1 degrees, if you calculate sin theta and then square it, you will get a value of 0.13. For 24.6, if you do the same, you will get 0.173. For 36.0, if you do the same, you will get 0.346, and for this, if you do the same, you will get 0.477. Okay. So, now at this point you try to identify integer fractions. Okay, because what we said is that sin square theta should be proportional to an integer. H square plus k square plus L square is an integer, and so sin square theta should be proportional to an integer. Okay. And so we try to identify integer fractions of each of these. Okay. Now we notice that you have 0.173 and 0.346. So, clearly this is twice this. Okay. Clearly 0.346 is twice of this. Okay. Now, and we see that 0.13 is about 3/4 of this. Okay. So, if we use 0.042 as the fraction as the divisor, then this will be 3 times. So, 0.13 is 3 times 0.042, 0.173 is 4 times 0.042, this is 8 times, okay, and this is 11 times. Okay. So, the integer fractions. Okay. So, this again we just inspected it and we identified these integer fractions. Okay. And now, so what we identify immediately, that h square plus k square plus L square, if it is 3, okay, then what that means is our h k L has to be 1 1 1. That is the only way h square plus k square plus L square can be 3. Similarly, if it has to be 4, it has to be 2 0 0, 2 0 0 or 0 2 0 or 0 2 0 or 0 0 2. This has to be 2 2 0, this has to be 3 1 1. Okay. So, we immediately see that they are either all even or all odd. So, implies it is a face centered cubic structure. Okay, it is a face centered structure, and since it is cubic, so it is face centered cubic structure. Okay. So, just by so this is how you index the peaks. Now, the remaining part is to calculate the wavelength, to calculate the lattice parameter. So, so again, if you use the expression sin square theta is equal to h square plus k square plus L square divided by 2a by lambda. This should be, sorry, this should be 2a by lambda. A by lambda, not a by 2 lambda. Okay. Then what you 2a by lambda, let me write sin theta is square root of h square plus k square plus L square divided by 2a by lambda. Okay. And if you work this out, okay, you will get now. Let us take the case where h k L is 1 1 1, okay, and for that we have theta equal to 21.1, okay, and if you do this, okay, you will get 2.456. Okay, you can verify this. Okay, so basically you will have root 3 and then you will have root 3 divided by 2. Okay, and so that will give you about 2.456. Okay, and if you substitute the value of lambda for copper k alpha radiation is 1.0 1.5418 angstroms for copper K alpha. Okay, so that implies, and this should be provided, Okay, I did not provide this in this problem, but it should have been provided. This implies A is equal to 3.71 angstroms. Okay, so we can calculate the lattice parameter in this way. Okay. Now, next problem, okay, this is a problem, okay, which says that electrons are accelerated by 50 kilovolts and these are bombarded on a piece of copper. What is the minimum wavelength of X-rays that can be produced by these electrons? Based on the result, is 50 kilovolts sufficient to produce the copper K alpha radiation of wavelength 1.5418, and what is the wavelength of the accelerated electrons? So, we saw when we were discussing X-rays that the minimum wavelength that is produced by X-rays that are produced from accelerating electrons, okay, by some voltage is can be written in this way 12398 angstroms divided by V in volts. Okay. And so if we substitute 50,000 volts so that gives me 0.28796 angstroms. Okay. So, clearly the wavelength is much smaller than the copper K alpha radiation. So, this is sufficient. So, the wavelength is smaller means the energy is higher than copper K alpha. So, basically this is sufficient to produce Cu K alpha radiation. Okay. And so, basically 50 kilovolts is sufficient to produce the copper K alpha radiation, okay, since the minimum wavelength is much smaller than the wavelength of the copper K alpha radiation. Remember that smaller wavelength corresponds to higher energy. So, it has more energy than required for the copper K alpha radiation. Okay. Now, what is the wavelength of the electrons? So, lambda of electrons is equal to 12.3 angstroms divided by square root of V, square root of 50,000. Okay. This works out to about 0.055 angstroms. Okay. And as we said this is much smaller than the wavelength of the X-rays. Okay. So, with these practice problems I will conclude this lecture, and with this I will conclude week 9 of this course. So, in week 8 and week 9 we have learnt a lot about X-ray diffraction, but we have also learnt about a few other things like reciprocal lattice and some microscopic techniques. In the next week I will look at crystal structures of typical materials, okay, starting with metals, binary compounds and some interesting oxides. Okay. So, this will be fairly descriptive, okay, but it will be interesting to see what are the various structures that are commonly found. Okay. So, thank you.